Really thankful that Chase invited me to give a talk here, and this is going to be, I sort of generalize this talk to talk about how we sort of process remote sensing data and innovations that we're trying to implement at in the Murray lab at Caltech in terms of processing data in a way that preserves as much information as possible. And it required us, when we were making this global mosaic of Mars that I'll use as sort of the case study here, to go back to sort of first principles about how we process and engage with and interact with visual information. So some of this might sound, I don't know, elementary, or maybe I've just been thinking about it a long time, so it feels that way to me. But we're going to sort of start with, get back into PowerPoint here. So when we take data from its raw format and then process it using some sort of processing pipeline to a derived product that we put out on the internet for people to use, and then those products go on and get used for science, we have varying standards in terms of how much information is communicated to the reader, where we have higher standards for traceability and reproducibility on the science end of things, and less clear standards about the processing pipeline. So what we were trying to do with the CTX mosaic is sort of balance this equation that if you're making a product, a derived product for the community to use, then our standards for traceability and reproducibility on the processing pipeline side of things should be as close to as possible what we use when we're actually conducting science with the data itself. So this is sort of the foundation of everything that goes into a scientific work. So how do we maximize the amount of information that we get from this pipeline part of the process? So to give you a very brief introduction to a very large project, we're taking over 100,000 high-resolution images of Mars with the CTX imager, between 5 and 6 meters per pixel across the entire planet, and trying to register them together and stitch them together into one seamless mosaic that the community can then act. That's an animation made by Malin Space Science Systems and JPL of the last 14 years of data being acquired from Mars, and we're just about at the stage where we have nearly 100% coverage of the planet. And you can see our preliminary version of the mosaic here on the right. So we're taking these individual orbits, merging them into one mosaic, but what we wanted to try and innovate with this, with our project, was to make it reversible in some way. So to take the mosaic and then link that back to the original data. So instead of just getting a mosaic that you can then use and take to do your science, we want a mosaic that you can use for your science, but also trace back to the raw data. And for planetary mosaicing, this hasn't really been done before. So we innovated a new technique that sort of built upon a lot of the work that's been done before, specifically with Themis, which has been really fantastic. So we're sort of augmenting what was done for previous mosaics. So when we get an image from Mars, it's important to think about it not simply as a grid of pixels. Each orbit that we get, or each image that we get, has 51, in the case of CTX, has 51 separate attributes that describe everything about the acquisition of the image. Where was the sun when the image was acquired? What season was it acquired? How was the spacecraft pointing towards the surface? Was it looking straight down or was it oblique? All sorts of information like that that goes into how we interpret what we see on the surface. So we want to preserve this information while making the mosaic of the entire planet. So that's just a small sampling of all the information that comes with us, with this. So these data are really valuable. We frequently use this information to determine whether a bright spot on the surface is frost or a light tone rock or something like that. You can tell based on the season what it's more likely to be by preserving that information. So the traditional way of taking raw data and processing it into a derived product is what we're terming destructive processing, where it's what you're all used to in terms of how Isis works, how GDAL works, in terms of a processing pipeline. So you have a file that may be 175 megabytes. You perform a function on it, create a new file to get it into Isis. From there, you would perform another function on it, maybe a radiometric calibration. You create another 175 megabyte file. You want to normalize it. These are just the steps that we use in the processing of the data for the mosaic. So you create more and more of these files, and you finally project it, and then you might contrast stretch it, compress it down, and you end up with your derived product. So you see the fan within Jezero crater, the Mars 2020 landing site as the sample there. So this is how we get data from a raw form into something that we use for science. But what we do is, instead of keeping all these 175 megabyte files as scratch, we throw it away, and that can have consequences in terms of what information is being lost, how you're degrading the quality of the data along the way. You just end up with this one product. And then hopefully you might write a paper about what you did and sort of provide a narrative about what you did to the data. But there's no direct connection back to the raw data and how you got from where you are to where you were. So the traditional destructive processing has limitations in terms of how much information you can retain while you're processing the data. And this is particularly true when it comes to blending data. So, and that's sort of the coin of the realm for mosaicing, is how do you take two images acquired at two different times and stitch them together in a way so that they look like one image. So in the past, how this has been done has been using destructive techniques of pixel averaging, ramping, and doing sort of cool stuff to sort of transition from one image to another to make it look like one image. But when you blend pixels like that, when you start averaging pixels together, the consequence is that you can no longer trace your data back to the original data. So we start with image 1 here, we blend it with image 2, but everything in the middle here, you no longer know when those pixels were acquired, because they're a mashup of multiple orbits. So you lose that information. So when I say destructive processing, you're destroying the information along the way. And this is just how we've done business for the longest time. So the artistic community and the proprietary software community, so this is not open source, has thought about this for a long, long time. And this is, go back into the literature, there's not a lot in the academic literature, but you can go find patents from inventors in the early 90s. This was originally submitted by a French inventor, Bruno Delant, sort of a legend in the commercial image processing world, about how we can interact with data in, he developed the term, non-destructive ways. And you go back into some of these patents, and there's a lot of the limitations that we have with current geospatial data processing are articulated here. So numerous image processing procedures currently exist. Common to all procedures is modification of an image through recalculation operations to irreversibly rearrange dots or picture elements, pixels. So irreversible. So at the state of the art in 1994 is where we're at right now with our destructive processing. So, and he pointed out the limits of image editing effects applied sequentially, step by step. So you get severe degradation in quality of the original image. So these are some of the limitations that we still have with some of the traditional ways that we process planetary data. We've sort of accepted them. But there is a better way, and it's non-destructive image processing. So we're going to start, and this is sort of my vision for how USGS Isis would behave if it was in a non-destructive framework. So as somebody who's not a developer myself, any developers on the line might want to take this as a challenge to take the open source software of USGS Isis and adapt it in a way that works non-destructively. Okay, what do I mean by that? So instead of a linear pipeline where you create successive generations, the step-by-step sequential image processing, you think of it more as detached functions or keys on a keyboard that you can press in different orders to create different products. So we have our raw image here on the left. This is a glacier off the flank of our Sea of Mons. And you have these functions, these sort of normal functions that take time to process our planetary data. And instead of processing them in order in a non-destructive framework, what you would do is apply them at the discretion of the operator. So you decide which functions you want to apply dynamically, and you create a new output on the fly. So this is all on the fly. And then you can turn functions on and off. So we take off our calibration routines. So we now are just projecting it. So now you can sort of see what's happening to the data in real time, and then decide at the end of the day how you want to export it, as opposed to developing successive generations that take up a lot of file space, degrade the data, lose information, so on and so forth. You do it non-destructively, you can preserve all that information as you go. So here's one where you turn off the projection from CAM to map on the fly. So you're seeing what happens to your data along the way, and you're always preserving information. This is how Adobe Photoshop works. So this is, Adobe has sort of developed non-destructive editing. They've sort of taken the lead on this. There's a whole language that goes with it. And this is because if you're a photographer, if you're an artist, if you're a graphic designer, preserving information is really, really, really important. So if you're creating something for a client and you want to show them 5 different options, it's less efficient to do the same thing 5 separate times with a linear pipeline. You want to create 5 different versions of the same thing with functions that are attached and detached. So I've always found this extremely elegant, and I was wondering how this could be used for planetary data processing in an information preservation context. And it turns out that Photoshop was the key to making the CTX mosaic work while preserving all sorts of information. And in this context, it's the way that Photoshop blends data. It does it entirely non-destructive. So almost all functions in Photoshop are non-destructive. They're fully reversible, preserving all information. And when it comes to blending data, instead of mixing pixels and averaging pixels here, you draw what we term a seam line between 2 images so that you're never mixing pixels. And it does this extremely efficiently, very, very fast, and can scale up really, really well. So we were able to blend about 225 CTX, full resolution CTX images at one time. And here's how it works. So when you take 2 orbits that were acquired with slightly different illumination angles, so here's an impact crater, sun coming from the upper left, that same crater imaged with sun coming from the lower left. So blending pixels wouldn't work here, but if you non-destructively calculate the path of least contrast between them, then you can connect the 2, and they're like pieces of a puzzle at this point. So you retain all of the information of each original orbit. You can convert those masks that are used for the blending to polygon shape files. So this is where the open source software comes into play by mixing Photoshop with GDAL, which does the polygon, the digitization of the polygons, and you end up with this. So these, what we call seam maps, and seam maps are sort of the lifeblood of the CTX mosaic in terms of connecting the mosaic's product back to the original data. So the seam maps provide pixel for pixel mapping of seams. So if you're curious about whether something is a mosaicing artifact, those are inevitable, or an actual feature on the surface of Mars, the seam maps will tell you that. But what's really important for us is that these are fantastic vessels for information. So every seam map that we have here layered over the mosaic itself can be linked back to original data. So we hyperlink them back to the ASU site, which has all the original data. So you can go back to the PDS instantly to get the raw data. So this is how we're connecting the derived product right back to the raw data, so providing full traceability back to the original data. The version of the mosaic we're working on now has image-to-image registration, and that can vary in quality based on various factors. So these seam maps are going to be vessels for us to communicate how well registered the data are, first image-to-image, so that they line up. You can tell, you get a root mean square error of how well aligned they are, then eventually how well they're tied to the actual ground, to a controlled product as well. So that's in the future. now communicate that information directly to the scientists on the fly with these seam maps, which were only possible by doing this non-destructively. So how does this play out for actual users? If you're in ArcMap, this works in QGIS as well. You have the seam maps over the mosaic. All that information, all 51 attributes are retained. Direct link to the ASU site, which they've just done a fantastic job of providing for free for everyone. Then you can go download individual orbits that are GIS ready. They have links to the PDFs, so you can go all the way back to the raw data, and then you can add that straight to your document. So within a matter of, depending on how fast you can download your data, you can add the original data or a less processed version, unmosaiced version of the data right to your document, and can compare the individual orbits, which have been modified much less, to the mosaic product in close to real time. So more efficient access from the mosaic product back to the original data that went into the mosaic. So any degradation that was incurred as part of the mosaicing process, you can go compare it directly to the original data as quickly as we can make it right now. So the way this all works is through ComTypes. ComTypes is a module, Python module that there's far more detail than I'm qualified to communicate now, but it takes JavaScript from Photoshop, or takes your Python command, converts it to JavaScript that Photoshop understands, and executes it within a Python environment that you can then use and connect with your traditional GDAL commands in a Python environment. So that's the bridge that brings us all together. This is developments from the digital arts community, the digital hacking community. So any sort of artists that want to sort of scale up their work with Photoshop, we're sort of leveraging all the work that they've done to make this happen. Photoshop obviously comes with a stigma for image manipulation stuff. We don't care. We embrace the stigma. It works so well for our purposes in this mosaic that we've thought about how not specifically Photoshop can be used, where you run into scientific limitations obviously with it, but whether the model of non-destructive processing can be implemented in an open source context. So I'm going to leave sort of the conclusion slide up here. And I think the open source software community could learn a lot from what's going on in the proprietary software community as well. And the inverse is, I'm sure, absolutely true as well, that in a visualization context, you need to retain information and have processes behave extremely quickly for a user. So everything that Adobe has done over the last 20 years has really improved this. And we're starting to see this bleed over into ArcGIS. There's some extremely highly functional, non-destructive techniques that are being implemented into ArcGIS, specifically with real-time image registration. Worry about that, but over the last 5 or 10 years, it seems like Esri has adopted a lot of the non-destructive techniques from the arts world. And for the moment, these techniques for ArcGIS, you can implement in Python. For other software, you can bridge with ComTypes, which is sort of the secret sauce for the CTX mosaicing. So from a big picture, I think that planetary data processing would benefit, in the open source community, would benefit from lessons of planetary data engagement. And if we can sort of bridge those two, there are a lot of side benefits, including scientists actually seeing dynamically what's happening to their data. I always worry about students just getting a data product and running with it and not understanding what was done to modify it to the form that they see it. So when we work with students, we want them to see what it means when you calibrate and radiometrically calibrate or run a column-based normalization. That doesn't mean anything unless you actually see it happening. And then there are benefits with efficiency that was the reason that non-destructive processing was invented in the first place. So we were able to do this all without high performance computing. It's done entirely on work stations and is incredibly efficient. And as a general concept, this provides fewer barriers to connect the scientist with the raw data. So fewer mistakes, better science, more efficient processing. And I did a screenshot of the website. There's more information about how we made this on the Murray Lab website. So I encourage you to go there or to ask questions to me now. Thanks a lot.
Thank you, Jay. If anyone has questions, you can just go ahead and unmute. And I will also just open up the chat to general kibitzing and after talk discussion. So thanks everyone for attending the lunch, and I'll open it to everyone.
Hi, this is
I'll
Michael.
also stop recording.